Hello, ladies and gentlemen. Today we're going to take a look at mass defect and binding energy, the second video in our series on nuclear physics. So let's take a look. Now, a little bit of review from last one. Our atoms are composed of protons and neutrons and electrons. In the nucleus, there are protons and neutrons. The protons should repel each other and fly apart because of the force of electrostatic repulsion, but they don't. So let's take a look at some of the reasoning behind that and what's going on. So the first thing I'm going to do is I'm actually going to start by taking a look at helium-4. This is a common and fairly simple element. All I've got here are 2 protons and 2 neutrons. Now, on our physics formula sheet, if you take a look at that, we can actually see that I've got a nice chart here at the top of this table here. From this, you can see the protons and the neutrons and the mass of those. You take a look in our class notebook, I will have the formula sheet in there so you can find these values yourself. If we look, we can see that the proton and the neutron have very specific masses. So let's use this and go take a look and see what the mass of helium-4 is. So if I go protons, I have the number of protons here. I know that I have 2 of those, so I'm just going to take that value times 2. I'm also going to take the number of neutrons times 2 because I have that as well. If I take these values, and be very careful, you should use all of the decimal places for nuclear physics, because if you look, if we were to only use 2 decimal places, the proton and the neutron have the same mass, so we need more precision here. Increased precision. In this case, they start showing up a difference at 3 decimal places, but for some things, it's quite a bit more than that. So we need to be careful and use enough decimal places. I took my protons here. I'm going to take that times 2. I'm going to take the number of neutrons times 2. So that works out to 3.3452436 times 10 to the negative 27. kilograms. Do the same thing for my neutrons, 3.3498548 times 10 to the minus 27 kilograms. We are dealing with very, very small numbers here, so please make sure that you are comfortable with scientific notation. If you're not, ask me and we'll go through this. But these you can straight up enter into your calculator. Now, this is the mass of 2 protons. That's the mass of 2 neutrons. If I add those up, so if I take those and I add them up, I get a total of 6.6950984. 984 times 10 to the minus 27 kilograms. Great. That's awesome. Now, this here is what we're going to call our calculated mass. So this is like saying I have a bag with 2 10-pound weights and 2 5-pound weights in it. I should have a total of 30 pounds of weight in this bag. So I look and I go, yep, here's my calculated mass. Awesome. Now let's take a look at the measured mass of helium. So if I go here to my table of isotope masses, and again, this table will be in the class notebook as well, so you can look it up. This here provides the isotope of these, or the masses of all of these different isotopes. So if I go here and find helium, this is helium-2, helium has 2 protons, that's the atomic number. Here is the mass, so helium-4 has this mass here. This here is the mass in atomic mass units, which is not super useful for us. So I'm going to go back and I'm going to find the mass of this in kilograms. We'll get to the atomic mass units in a little bit later. So if I look at the mass here, I'm going to look up the mass of helium-4. My measured mass, when I look that up, I find that the measured mass is 6.6447 times 10 to the minus 27 kilograms. So my measured mass in this case in kilograms is here. My calculated mass is here. Now, take a look at these numbers and notice that these numbers here do not match. This should be weird. This is like having two 10-pound weights and two 5-pound weights in a bag, and you pick up the bag and find out it's only 27 pounds. There's mass missing somewhere. This measured mass is less than this calculated mass, and that is huge. This is really, really weird. So let's find out how much mass is missing here. If I take a look at this, I'm going to find my delta M, or my change in mass, and I'm going to take my calculated mass, and I'm going to subtract my measured mass. So to find how much is missing, I'm just going to take this minus this, pretty straightforward. And my missing mass here works out to be 5.03984 times 10 to the minus 29 kilograms. In other words, we have this much mass that is missing from the nucleus of the helium atom. And this is weird. We should have this, but where did it go? Here's where this gets interesting. We're missing mass, but you remember, there should be something holding this together. Our protons should fly apart because they repel each other. They don't. What's providing that force? Now, in physics in grade 12, we're more concerned about energy than force. You remember work and energy and kinetic energy and potential energy and all of that. There's something providing the energy to hold this together. And in fact, this missing mass is present in the energy holding this together. So this here, this missing mass has a fun word, fun term, the mass defect. The mass defect is the missing mass in the atom when we try and calculate what it should be versus what we measure it to be. Now, here's where we get fun. This mass, we can convert that to energy. We have a way to convert how many kilograms of mass I have to how many joules of energy that is equivalent to. And this is where we get to use probably the most famous formula in physics, which is E equals mc squared. So here's our new formula, E equals mc squared, or delta M, because that's the mass we're looking for. This here is Einstein's formula, and this is extremely famous. Now, note, our speed of light here can approximate as 3 times 10 to the 8th meters per second. We square that, we get 9 times 10 to the 16th, which is a big number. 1 kilogram of mass is 9 times 10 to the 16th joules of energy. That's a huge, huge number. However, we're dealing with a very small mass here, but we can convert this into joules. So if I plug this in, this formula here, I can say my energy is going to be 5.03984 times 10 to the negative 29 times 3 times 10 to the 8th squared. Be careful with your bed mass on this one. Make sure that you do that squaring first. And what I work out to here is the energy. If I convert this missing mass into energy here, I get 4.5358. 560 times 10 to the negative 12 joules. That seems like a very small amount, but remember, we're talking about a nucleus of a helium atom. This is a very, very small thing. That is a large amount of joules for that thing holding this together. So this here provides the energy for sticking that together. It has to overcome that energy in order to escape. So this here is what we call our binding energy. Okay. And this is important because E equals mc squared converts, if I have my mass in kilograms, this converts it into joules for my units. We'll look at other units later, but converting kilograms into joules, this is my binding energy. Now, this here is expressed in joules. We can use other forms of energy here. So here's my mass defect. If I want to talk about my binding energy in another unit, which is very common, which is MeV, I can do that as well. So I'm going to convert this, and then we'll talk about what MeV means. So to start off with, I have, I can need to convert this into electron volts. So the idea is 1 electron volt is 1.6 times 10 to the negative 19 joules. That number should look really familiar. That is the charge on an electron, because an electron volt is the amount of energy required to move 1 electron across a potential difference of 1 volt. And that should sound really similar to work as force times distance, because it is very similar to that. So our units of electron volts, 1.6 times 10 to the negative 19 joules. Another thing that's useful to know is that 1 MeV, or mega electron volt, or million electron volts, is 1 times 10 to the 6th EV electron volts. And again, that's pretty standard. This is just our mega prefix from our SI units. So these are important conversion factors. If I take a look at my formula sheet, you can actually see that these formulas are on here. So I have my electron volts here, and then my mega electron volts is just there. But you can see I have a mega electron volts as amount of energy here. So let's convert this. I'm going to take this energy, 4.535856 times 10 to the 12, divided by 1.6 times 10 to the negative 19, and I end up with 2.83491 times 10 to the 7 electron volts. And I can take that, 2.83491 times 10 to the 7 divided by 1 times 10 to the 6, and I get 28.3491 MeV. So there's my binding energy in million electron volts. This here is often more common. We, in fact, are going to talk about million electron volts more frequently than we will use joules throughout this unit, because this is a easier number to relate to. It's easier to say 28.35 MeV than it is to say a bunch of joules with scientific notation, because scientific notation isn't very fun to say. So MeV here, this is the binding energy in million electron volts. We can convert using these here. These are our conversion factors. They are on your formula sheet as well. We also have our mass defect and our binding energy. So, quick review. When I calculate the mass, I multiply the number of protons by the mass of a proton. I multiply the number of neutrons by the mass of the neutron. I add it up, get a calculated mass. This is what it should weigh. I subtract the measured mass to find the mass defect, what's missing, the missing mass. I can convert that into energy. If I have it in kilograms, I can convert it into joules by using E equals mc squared. If I have it in atomic mass units, I can convert it into MeV. We'll do that formula tomorrow. If I have, or once I find my binding energy, that's the energy that is holding this nucleus together. And I can convert that from joules to MeV or back again if I'd like, using these conversion factors here. So I hope that you have a great day. Enjoy this new look at physics. Take a look in our class notebook. A copy of all these notes as well as the formula sheet and the mass table will be there. Have a great day.